Hola amigos! Today I bring you another extensive tutorial where we are going to see a cool technique that can be used to create effects like the ones here and much more. To understand what we'll be doing, let's look at these three effects for a moment. They have been made in different ways, but they all share a thing in common. They run some math on their contents, pass the result to other parts of the effect, and then save it into themselves, iterating recursively over time. Traditionally, this has been done in multiple render stages, which requires writing code to save the information in different buffers. The public website ShaderToy has plenty of examples of beautiful fluid simulations, like this one here, Chimera's Breath, made by tech artist Nimitz a few years ago. If we take a peek at the GLSL code, we can see that it uses 4 different buffers to achieve the effect, one to solve each fluid and one to combine them. On the other hand, the Niagara content examples use a unique Unreal feature called simulation stages, which allows storing these same image buffers as particle properties and running code on them. Doing something like this, writing rendering code in Unreal, would technically be possible, but could take a long time to prototype or need a new custom UI to edit and set up later. The advantage of the method I'll show you today over either of those two is that it can be done using standard materials and blueprints, which can be easier to use for many artists not proficient in HLSL. And now, with the introductions done, we can jump into a simple scene and start working on our effect. The first things we need are a render target texture and a material to display it to help debugging the results. This texture will hold the density of the effect and will be the primary buffer where we will apply our advection turbulence. The debug material will be very simple. Just set to unlit with a single texture sampler outputting our render target to the emissive color. On the render target texture, I'll just up the resolution to 1024 by 1024. Now we need to create a second material, which will be the brush that we will use to paint our density. This one is very similar to the previous material, only has one texture sampler, and I think I have some Guy's sprite that we can certainly use as a brush. In the material properties, set it to unlit as well, but this time set the blending mode to masked. This image has already its own alpha, so we might as well use it. The only other thing that you need is a blueprint actor to run our material passes. For these examples, I'm using a simple pawn with a movement controller, but you could run this on any type of blueprint. Another thing that is specific to these examples and you might not need on your own project is that I added a couple of input actions to have an easier way of showing some of these effects, like a paint toggle. For the first example, we'll use a line trace from the camera position. This will make it very easy to find the UVs where to paint our brush, but to make it work, you need to enable the feature in the project settings. Search for Support UV from Heat Results and enable the checkbox. Once the editor restarts, you will be able to use the Find Collision UV to get texture coordinates from heat results. Now create a new function on the blueprint. This one will do the camera trace and draw our brush if it finds the canvas, and we'll come back to it in a moment. We'll also need 2 variables for now, a boolean to know if painting is active and an actor to be our target surface to paint on. The node layout for this blueprint is quite simple. On the paint input event, we'll set the boolean variable true when the button is pressed and false when released. On the tick event, if this bool is true, we'll just call the shootPaint function. And that's it. We can test for errors, but this shouldn't do anything just yet. By the way, the actor reference needs to be set in the instance, so let me go back to the main viewport for a second and assign this inconspicuous red box to be our canvas paint target. Back into our shootPaint function, the first thing to do is the line trace. I'm sure that many of you are familiar with this concept, so I'll just quickly go over the basics. The trace will go from an origin to a destination point and return the first object encountered on this path. In our case, the origin is the position of the player actor and the destination is that same position plus some distance in the actor's own forward direction. Feel free to pause the video and take a look at the node layout if you need to take a second here. Note also that this is an extremely simple setup. In a real game scenario, you could need to offset these positions if your camera is not first person, for example, or the paint is coming from a specific in-game object. Let's enable the trace draw debug as well to make sure that the lines are going where they're supposed to be. And after the trace, we're going to break the hit result and compare the actor with the target canvas property. If they are the same, for now let's just get the texture coordinates using the find collision UV node and debug print the result. Oh, and I almost forgot. You need to enable the trace complex option in the line trace. Otherwise the get collision UV node won't work and always return a 0, 0 vector. Now we can set a distance value. 4 or 5,000 units is a good number to start, and see if all of this is working. Perfect. The traces are going in the correct direction and there is no text output unless we hit the canvas. And in that case, the coordinates go from 0, 0 in the top left corner to 1, 1 in the bottom right, as one would expect. Since everything is working, we can get rid of the debug traces and get to the meat and potatoes of the matter. We're going to need 3 nodes here. The first 2 are begin and end draw canvas to render target. For now, set the target on the first one to our density texture. We'll see how to create targets dynamically in a future tutorial. These 2 nodes define where our painting is going to start and end. And between them, we'll add a draw material, which will add our brush to the current context, which in this case is our render target. In this node, set the render material to the brush from earlier. In this tutorial, we won't be changing properties dynamically, so we don't need to create an instance of this material. As for the rest of the properties, the main ones that we need to set are the screen position and the screen size. This will determine where in the quad is our brush painted and how large will it be. For position, first we have to multiply the render target's size by the UV coordinates to convert them to the correct scale. Then, since our brush will be painted center in that position, we need to subtract half of its size. For this example, we'll simply set the size as a vector 2D variable in the blueprint. This size will be in pixels, so we don't have to scale it and can be plugged directly in the screen size property of the draw call. Let me finish connecting everything here and then we can give it a test. Here I'm just checking the size of my guy brush to make sure that when we paint it, the sprite has the correct proportions. We could automate this and get the actual size, then use a factor to scale it, but this video is probably going to be already close to an hour long and there is no need to add insult to injury. If everything is correct, you should be able to approach your canvas and start spraying your brush on it. Perfect. And since the texture is already on disk, we can close the game and it will stay there. This can be useful for a lot of applications, but for this example, let's add a clear render target 2D node just after the begin play event to reset the canvas every time that we start the game. Let's recap what we've done while I finish this part. For now, we just have made a dynamic texture that we can paint on. But Enrique, there are other tutorials that show how to do this, you might be saying. And I don't have a prize for you, but you would be correct. The main reason why is that the draw canvas to render target operation is the base of this effect, so I thought it was a fun way to paint our density texture and get familiar with this node in case anyone needed a refresh. With this setup done, it's now time to add a material stage in which we will manipulate our painted image. We'll start by adding a second Boolean variable to the blueprint. This one will control whether or not the effect is applied. Instead of using both the press and release events of our action input, this time we'll simply set the bool to the opposite of its current value on release, to make it work like an on-off toggle. Next, after the shouldPaint function, we'll check if this variable is true, in which case we'll call a new function that I named addTurbulence. If you're following this tutorial along, don't forget to also connect this branch to still be run when no painting is happening. Once this setup is complete, go back to the shouldPaint function for a moment. We can copy these three drawing nodes and paste them in the new function to save a few seconds. The only changes for now are going to be in the draw material node. Since we're going to paint the render target onto itself, the screen position can be left as 0, 0, and the screen size is the same as the render target size. The other change will be the material. Create a new one and name it something like Turbulence Stage or similar and assign it to the property in the draw material node. The reason why we went through all this setup is that this is the only way to read from the render target, do something with it, and then write it again into the render target, which is precisely what we've been after since the beginning of the video. And now, let's jump into the new Turbulence Stage material so we can make this magic happen. First of all, you will need to create a copy of this noise material function that I made and which we will probably use in future tutorials as well. This is a version of a fractal Brownian motion function made by combining layers of noise at different scales. After creating this function, you can drag and drop it from the browser or add it to the SER library so it shows up when searching node functions. Note that the first node is not a sampler, but a texture object using a volume texture. The specific one that I'm using here is available in the Experimental Volumetrics plugin content. You can use that one or find a different volumetric noise texture of your own. The three inputs below, from top to bottom, are first, a three-dimensional vector for position. We're going to sample from a volume texture, so we need three spatial coordinates. The default value for this one is the absolute world position. The next two are two floats, one for amplitude and one for fall off. You can copy my default values or try new ones. The main part of this function happens in the custom node. Here we are using a 3D sampler to get values from the texture 3 different times, each time at different distance and scale, before returning the result. You could create this effect entirely using nodes, but the iteration part could get a little messy. I'll give you a moment to finish copying this code before going back to the material stage. This material domain can be set to unlit just like the other ones that we created so far. After that, we'll begin by getting the texture coordinate and multiplying it by a scalar parameter. This one will control the scale of the Brownian noise. Next, we are going to take the time, multiply it by another factor to control the speed, and then combine it with the scale UVs to form a three-dimensional vector. This would let us use it as the position input in the noise material function that you just made, making it evolve over time. After adding the custom function and connecting the position input, we can temporarily output this as our emissive value, just to see the trippy colors while we keep working on this material stage. Okay, enough of that. Now we're going to add some detail to this noise. We'll start by adding the scale down time to it, before using component masks to separate the red and green channels. We'll combine these two values in a moment, but before that, we'll take the sine of the green channel and the cosine of the red channel, just to add another layer of cumulative distortion. After that, make a vector 2D with these two components. If you've made shaders like fire, plasmas or similar, you might have an idea of where this is going. This type of distortion is frequently used to make effects such as those, replacing the default UV coordinates with moving 2D vector values like the ones that you see here. Let's add another scalar parameter. We can multiply it by the noise to control the strength of this distortion effect. Next, we'll take this noise and add it to the original UV coordinates. And now that we have scaled and distorted UVs, we can feed them to a texture sampler using the density render target texture from earlier. After that, the final step for now will be to multiply the final value by a lower than 1 number to have the effect dissipate over time. We'll also expose this number as a parameter so we can change it later if necessary. Once you're done, double-check your notes one more time and give it a try. You should be able to paint your brush on the canvas and turn on and off the turbulence effect when you press the button bound to this action. I think this is already a cool looking effect, and you could spend lots of time just tweaking the parameters and get completely different results. If you want to do a proper fluid simulation, you'll need to add stages for density, flow, pressure, etc., and that is very much outside the scope of this tutorial. It would take more than one video to cover properly. And you could let me know in the comments if that is something that you want to see in the future. Something that you might want to change is if the effect wraps around the edges or not. To do so, simply change the address mode in the render target texture parameters. After changing the setting, the effect now appears on the other side when it moves beyond the edge. Let me quickly edit some of the settings on the material and show you something that looks more like someone dropped this painting in a bowl of acetone. Now, those of you who know about shaders might be still confused about why are we going through the trouble of doing this in a render target using the blueprint to draw it instead of just doing this math in a regular material. Let me show you with a practical example. I'm going to duplicate the paint canvas, but in the second one I will just assign the turbulence stage material. Once I add some paint and get it going, at first they look the same. However, once I stop the turbulence in the blueprint, look closely at the one on the right. it is doing the distortion, but the modified texture is not written back into the render target, so it just cycles with the noise. What the blueprint is doing is allowing us to save the render target, so in the next execution frame, the effect is accumulated over the previous result, instead of being applied to the original painting. Let's move on to a different use of this technique. First, I'm going to duplicate the brush and replace the Pirate Wannabe sprite with a simple snowflake. I added an interior gradient to it, so we can use it later to generate a normal map from the image. This image also comes with its own alpha channel, so we don't have to worry about opacity, just connect it to the mask output. We can give it now a quick test in runtime to see how it looks. You will notice that I also changed the Turbulence stage settings to get a bit more of a frost melting look. This time we're going to use this render target in a post-process material, so we need to create a post-process volume and set it to unbound, so it doesn't depend on camera position. Next, create a new material, set its domain to post-process, and assign it to the volume that we just created. I'll give you some time to get this done. Once you assign this material, your screen will go black, because the post-process is just returning 0. Let's fix that first so we can see what we're doing if we have to move scene elements around. We can do that by simply adding a scene texture node and setting the ID property to post-process input 0, which corresponds to the final scene color. After that, we have once more a viewport that we can work with. Now we need another texture object. Add one and assign it our density render target. Remember, don't use a texture sampler because this next function also needs an object input. The function we need is called normal from height map, and it does exactly what its name implies. It uses derivatives of the height gradient to calculate the slope in the texture and output the normal to it. Since the snowflake sprite has an interior gradient, this will give our texture the appearance of having beveled edges once we use it to distort the scene color. I'm also adding some parameters to override a couple of the default input values, just to increase the intensity and tweak the UV offset later. Let me output this temporarily and get some sprites in the canvas so we can see the calculated normals. Perfect, this is exactly what one would expect. The normals look crisp and nice, and since we use the built-in function, they are in the correct format for the engine. Let's see next how to use this to simulate a refraction effect, like ice crystals forming on the camera. With a different brush and some tweaks to the turbulence function, you could also use this to make a water droplet effect. If you wanted to go the extra mile with it, you could even add the camera or player movement to the map as an offset to move the drops in the opposite direction. And with even more work, you could add a second stage where the water was pushed and could accumulate, which would be in turn driven by a mask to make car wipers. In our case, since these normals are aligned with the view and therefore in the correct coordinate space, we won't have to do any trigonometry here. Simply use a component mask to get the red and green channels together, and multiply the result by a new scalar parameter, just to have some way of controlling the amount of refraction added. After that, it is just a matter of adding this value to the texture coordinate UVs before feeding them into the scene texture node. If you have done everything correctly, when you paint on the canvas, you should get copies of this sprite refracting the image from the camera. Let's give it a try now. This is starting to look good, but the snowflakes are dissipating so fast that the effect is a bit underutilized. This type of simulation has the best results when the densities are given some time and movement to interact and mix with each other. To be honest, if you just want a masked sprite fading with some texture, there are easier ways to achieve the effect. So let me play with the settings for a bit and see if I can find some quick way to improve the results without adding too much length to the video. Be right back. I only spent a few minutes off camera, but here's what I got. Instead of being placed in UV space using line traces, the brush is placed in a random position in the quad. I also added a small vertical offset to make the flakes fall downwards, and adjusted the settings a bit, mostly to slow down the dissipation rate and increase how far they expand from the source. Let's spend a moment to review these changes in the blueprint and material editors. We'll take a look at the event graph first. I removed the call to the should paint function and instead replace it with the one that you see here, add to screen, which runs every tick if the effect is active. The Boolean toggle works the same way as before. Let's also remove this first useless branch so it doesn't confuse anyone. The add to screen function is almost identical to the should paint one from earlier. I removed the line trace and replaced it with a cooldown check to stop it from adding a snowflake every frame and do it instead once every 0.1 second or so. The other change is simply using random float values for the size and position of the texture, making sure that they are scaled to the rendered target size. Finally, I created a vector offset parameter in the Turbulence stage material, which is added to the UVs of the texture sampler after masking its red and green components. Since the effect is accumulated, we don't have to factor in the time like we would do to pan a texture. We're just one effect away from finishing the video. We'll need one more brush, but this one will be a bit different. Instead of using an image file, we'll make a circular gradient using the node available in the Unreal Material Editor. I will also add a density parameter just in case that I want to change the scale of the gradient later on. You should also consider switching the blending mode of this brush to additive in the material properties. I will forget about it now and spend some time later trying to figure out why the masking is wrong, so better save yourselves the trouble and change it now. So far, we've looked at ways to place our brush on the canvas from a camera trace, or get in a random position on the screen. For this last example, we're going to get the position of an object in world space and project it onto the camera plane. You could use a blueprint component if you want to extend this effect to different objects in your game, but for this example, we'll keep it as simple as possible and use a single actor. This one will be responsible for projecting its world location to screen coordinates and painting the brush there. I've added a sphere to have a way to see this object in the scene, but other than that, this will be an event graph only blueprint. A fun way to extend this effect could be to use the object's velocity to drive the effect's dynamics, but we'll leave that to a future video. Let's copy our familiar by now set of draw canvas nodes from the other blueprint and paste them here, and then update the material to use our new soft gradient brush. I'll make some room here and add the first obvious node that we'll need, called Project World to Screen. This useful node has a very straightforward name, and you might be already familiar with it. We need to give it a player controller input so it knows which viewport to use. The output of this function is a vector 2D that we have to divide by the screen size to convert it to a 0 to 1 scale, and then multiply by the rendered target size. I'm also going to forget to do this last bit now, but you know the deal. I'll come back to it later if you just want to follow my moves step by step. After that, much like we've done with our previous brushes, we need to center the image on the target point, so we have to subtract half of its size. We'll figure out how to calculate this size in a moment, but before doing so, let's get the world location of the root scene component of this blueprint and plug it into the position input of the function. Here's a sweet trick to find out the approximate size of an object in screen. Get the object bounds, multiply them by a factor, then divide that by the distance to the camera, and finally multiply it by the sine of the camera's FOV. In our case, the field of view of the default camera is set to 90, so we don't have to worry about the last part. For this example, we can use the sphere radius output of the getComponentBounds node, but you could use stencil masks if you need more precise transparency management. Note also that the size that we are calculating is a screen percentage, so it needs to be converted to the correct scale, multiplying it by the render target's size. Since this viewport and the render target don't have the same size, we should scale the texture by the screen's aspect ratio as well, otherwise the texture will be deformed. Seems like I was getting tired because I also didn't notice that until a bit later, when I was trying to figure out why some things were not working as they should. Before connecting all of this to the tick event, we are going to use a branch, so we only paint the brush to the canvas when the object is within the screen bounds. If we do that before scaling the position, we can compare it against 0 and 1 values, making this task a tiny bit simpler. Once all of this node graph spaghetti is connected and ready to go, we can test it, and in my case, spend a couple minutes debugging the error. I fixed it off camera, but I'll go over the couple changes that I made to the graph in a second. These are the 3 nodes that I added while you were not looking. The first one scales the position coordinate to the scale of the render target. The second one divides the targets by the viewport sizes to get the aspect ratio between them. And finally, this aspect ratio is multiplied by the size to correct the values scale. Apologies for the errors, I hope that this wasn't too confusing. And finally, with the blueprint errors gone, we can jump into the game and see how is this looking so far. I spoiled this surprise earlier in the video, but this is what can happen if your transparency or blend modes are not set correctly. Each new instance of the brush is erasing the contents behind its quad, leaving some ugly rectangular shapes in its wake. To fix it, we could use the gradient itself as alpha value or mask, but for this example, we'll change the blend mode to additive. This will make it so only the bright parts of the brush contribute to the density value when we paint it into the render target. Once this other small mistake is fixed, we can give it another try. And this time it seems to be working as intended. It kinda looks like we have an on-screen brush, but remember, we're tracking the position of that small sphere on the screen. The snow effect from earlier is making things a bit harder to see, so give me a moment to remove that function call from our main blueprint. Done. We can take a better look at the effect now. And as we can see in this version, changing the mode to additive meant that we can keep painting over the same spot, and the normals keep increasing in slope, giving the impression that the fluid is accumulating on those areas. I think that we have a pretty fun effect already. I could keep playing with this for quite a while. adding features and tweaking its settings, but it's time to move on to the last part of this effect, where we're going to add some color tinting using the normal direction. Okay, maybe just a bit more, and then I'll go back to the tutorial, I promise. Okay, we're back in business. For this last part, we can reuse most of the post-process material that we made before, so just duplicate that one and give it a new name. Fun fact, when I posted a short clip of this effect on Reddit, more than a few people mentioned that this reminded them of a migraine, so I named it just that. And remember to update the post-process volume with a reference to this new material, otherwise you'll keep seeing the previous effect. The next part is a bit complicated and a bit messy, but just bear with me for a moment while I add a bunch of notes and I will try to more or less explain what I'm doing. This is a simpler version of a formula used by tech artist Leon in one of their shader toy demos, and produces a nice rainbow effect that has some interesting potential uses. First, we are going to calculate the dot product of some color and the normal map, before scaling the value and adding that to a secondary color. This will give us different tints based on the slope of our density gradient, creating the illusion of some kind of light bending effect. Next, we'll calculate the cosine of this result, convert it to a vector 4D, and finally add it to the scene texture. Since we are going to have negative values offsetting the original color, we have to clamp the final number using the maximum of itself and 0. If this last chunk of information sounded a bit confusing, don't worry, you're not the only one who felt like that at first. It took me some time and experimentation to understand what was happening inside that equation. For the purpose of this tutorial, however, you can simply follow along and copy the node layout that I'm using, and afterwards start changing the values and numbers to fully understand how it works and make your own version. And now please stay with me just a little longer so I can finish this graph and test this last effect before ending the video. This looks pretty psychedelic, but all in all, I think it's a neat effect, the kind that you don't see often in video games. And more importantly, we've learned about material stages, the foundation for tons of really interesting effects of all kinds. And much like before, I could stay here and play with these settings for hours and hours, trying different color combinations or adding multiple objects with different brushes and so on. But I think that this video is already too long, so I won't take much more of your time. At first I thought that this video was going to be an hour long, but I managed to shave a good chunk of the total runtime. Anyway, if you stayed until the end, thanks for watching the video. I hope that you find this content useful in your projects. See you next time!